In this video, we're going to consider how to do some sensitivity analysis. Let's begin with our familiar Vibrio parahemolyticus in oysters model. And I'm going to scroll on down to our output. I'm going to do a simple simulation of 10,000 meals. Now, ordinarily, what we would do is begin with some importance analysis, taking our output and using a tornado graph. So we now have a completed output. You see the mean is 0.0017. So for this particular set of 10,000 meals, 17 people got sick. I have a very small positive output. There's a tiny red dot of ones, but mostly zeros where people didn't get sick. If I click on the tornado graph, let's say regression coefficients, we get nothing of value. So the tornado graph is going to be useful in some models, but not in all models. So at-risk has advanced analysis that you can do. Let's investigate this a little bit. The very first thing that you see here is goal seek. When I click on goal seek, you'll see that previously what I had done is I said I would like to investigate cell E44, which is our output here, and I would like to know what does it take to make output equal to 1. In particular, I would like to know what does it take to make output equal to 1. Whoops, I can't quite show you cell E17, so let me close that and now try again by changing cell E17, and that is the time unrefrigerated. Well, I'm going to spare you this analysis because when I hit analyze, it runs 100 simulations of 10,000 iterations each, and it basically comes back and says if the time unrefrigerated is 62 hours, then the person's going to get sick. The value will equal 1 in E44. So having oysters unrefrigerated for 62 hours is hopefully never going to happen. That's a long time sitting on top of the deck of a workboat. So we're going to ignore that for here. But what I would like you to understand is that you could use this as the same sort of goal seek that Excel has. If you have a value in your model that is of interest to you, you identify the cell where the value is found, you identify the value that you're interested in, and then you select one cell that can be changed to make this cell equal the value of interest to you. And as I said, using time unrefrigerated, it would take 62 hours for cell E44 to equal 1. So let's cancel that. That's not so terribly interesting. Go back to advanced analysis, and there's something called stress analysis that you can do. So for stress analysis, essentially what I did was I went into the model and I said, take a look at E44, and I am interested in two variables in particular, E17, which we've been talking about here, that's the time unrefrigerated, and E10. Now E10 happens to be the water temperature. So now we're going to take a look at options. We have two different variables, and I'm asking at-risk to stress each input in its own simulation. I'm requesting some graphs here, but as you'll see, because of our model, these graphs are not going to be terribly interesting. Okay. Now I'm going to go over here and I'm going to say, take a look at this first value, and I opened it up. It's E10, that's the water temperature, And what I want you to see down here is the variation. We have a method to choose here, and we can stress low values, high values. You can use a custom range of values, or you can put in an entirely different distribution. So basically what we're doing with the stress analysis is we're going to say, when you get to water temperature, I would like you to do all of the sampling from low values. Don't sample from the entire distribution anymore. And in particular, I'd like you to take all the samples from the 0th percentile through the 5th percentile. So we could change this in any way we like to take values between any two percentile values. So I'm saying take only the lowest temperature values here. And I click OK. And now I'm going to take a look at E17 and edit that. And this says E17 is the time unrefrigerated. And then once again, I say just sample from low values. Notice we could sample from high values, and I can put a custom range in. If for some reason I wanted the 30th percentile through the 37th percentile, I could put that in, or I can put in a new distribution. So I'm saying use the distribution that you have, but only pick the low values between 0 and 5%. Now the reason I'm doing this is I'm curious. I would like to know if we could restrict catch to times when the water is cool. How effective would that be in reducing illnesses? Or if we could restrict the time that watermen leave the oysters unrefrigerated, how might that affect the number of illnesses? So once I get my model set up, I hit Analyze, which I've already done. So let me switch out for you here. And this is the output. Notice that when we have no stressing going on, we have a baseline measure, and the mean is 0.0013. On average, we get about 13 people sick. Now, with all the other values the same, except water temperature is going to be between the 0 and 5 percentile values. So it's taken all the samples from the lower 5% range of that distribution. Then we find that the number of illnesses drops from 13 per 10,000 to 5 per 10,000. And similarly, if we let everything be the same as in baseline except for the time unrefrigerated, we get a drop from 13 per 10,000 to 5 per 10,000. When we go to the comparisons, you get some graphic measures of this. This is the baseline risk. If we had cool water, the risk would drop to this. And if we had unrefrigerated time restrictions, we could drop the illnesses to this. The other tabs are not so interesting, and that's primarily because our output range is such a small number that these box and whisker plots don't turn out to be terribly interesting. And the same is true for the histogram and CDF, but that's more a function of the model that I'm using. For other models, these could be very helpful kinds of graphics. So I'll skip showing you those others and return to our model here. So the next thing that we might want to do is take a look at the advanced analysis, the advanced sensitivity analysis. When I click on this, I get the opportunity to monitor the results of cell E44, that's my number of illnesses, and this time I'm using water temperature, same as we did before, the time unrefrigerated, the same as we did before, but I'm now adding a third variable, the length of refrigeration time. That's right here. Once again, if we edit here, we're going to see that we've got, for E10, we're going to be looking at a range of percentile values. We'll look at the 1st, the 5th, the 25th, and so on, so forth. The same would be true for these other variables, so I will spare you that. The options that we're using here, we are asking for some specific kinds of reports, some specific graphs, and we've asked them to be put in a new workbook. Once you have the variables selected, click on the Analyze, which I have previously done, so I'm just going to go to those results for you. These are the results from the Advanced Sensitivity Analysis summary. So let's take a look at what we have here. We've got water temperature. These are the values found in cell E10. So from here down to here, I have water temperature values. So they use the 1st percentile, 5th, 25th, 50th, 75th, 95th, and 99th percentile values for water temperature. These are the actual values that were used for the water temperature. And this is how water temperature affects the illness rate. So you saw earlier that the mean was 0.0013 or 13 people. If water temperature comes from the 1st percentile around there, the water temperature would drop, would decrease the number of illnesses to about 6 per 10,000. You see 8 per 10,000 here. But let's take a look as the water temperature rises. As the water temperature rises, once we start looking at the 75th percentile and above, we have 17 people per 10,000. Then 23, and then finally 31 people per 10,000 would get sick if the water temperatures were very high. We look at time unrefrigerated, and these values are shown right here. You can see if we can get the oysters refrigerated quickly, the illness rate drops rapidly from 13 per 10,000 to 3 per 10,000. If we take a long time to refrigerate the oysters, the rate rises from 13 per 10,000 to 30 or 32 per 10,000. So we're getting some advanced sensitivity analysis here from this particular feature. We're looking at the length of refrigeration time. And here we're getting an opposite effect. If the oysters are not refrigerated for long, then the illness rate rises from 13 per 10,000 eaters to 24 per 10,000 eaters. And if we have a relatively long refrigeration time, then the number of illnesses drops. There are a couple of other graphics here. This is a spider graph. Here they call it a percentile graph because we have percentiles on the horizontal axis. On the vertical axis, we have the illness rate. So this is 5 per 10,000, 35 per 10,000. When we look at water temperature, we're basically seeing that as the water temperature increases, the rate of illness increases. Okay? For time refrigerated, that's this reddish line. You see that as the time unrefrigerated increases, the illness rate increases. The higher you are, the greater the illness. So this is showing us that time unrefrigerated is a more sensitive variable than the water temperature is. It yields higher rates of illness. And that happens once we get above the 50th percentile. Below that, we would see just the opposite. Their water temperature produces the highest rates of illness. Green is the length of refrigeration time, and it has an opposite slope. It's basically saying that low numbers produce high rates of illness, high numbers produce low rates of illness. This is with percentile. If we take a look at the percentage change from the base value, looking at the data and the same data in a different way, we see results in a little bit different light here. The range of results, looking at the vertical, in water temperature, you don't need much percent change in water temperature to get fairly dramatic rates of change. We need more dramatic changes in the time unrefrigerated to get similarly dramatic changes in the illness rates. And for the green, you also see the negative slope there. So these are different ways to take a look at your data to find out which variables have the greatest impact on your output. There are additional graphics here. Time unrefrigerated, you again see the box plots, but the box plots are not really revealing much information because of the scale here. The numbers are very close together. I played around with one of the graphs here and changed the scale so that you could see that the box plots are actually located in different positions, but the scale is such that when we look at the default ranges, they provide no useful information. And we have an output here that's either a 0 or a 1, so a box plot's not a particularly revealing kind of tool. So what you've seen here is, for a model, any model, you can use the basic importance analysis where you run the model and then look at the tornado graph. That was not useful here. We went up to advanced analysis and found out goal seek is sometimes useful. It was not particularly useful in this model. We were getting rather ridiculous numbers that were necessary to ensure illness. We looked at the stress analysis, which enables you to limit the sampling from selected distributions to specific ranges so that you could see what happens to your outcomes if you stress the inputs. And then we just looked at the advanced sensitivity analysis. So that gives you 4 options within at-risk for doing some sensitivity analysis.